got two rational expressions multiplied. So how I'm going to approach these problems, I'm going to understand that since these are being multiplied, I can push everything together on top, I can push everything together on the bottom. But as I push these pieces together, I should probably make sure these pieces are factored as much as possible. So I look at this 3p minus 6. First rule of factoring, take out the greatest common factor. I take out a 3. If I take out a 3, a p minus 2 remains. Continuing across the top, you've got the p squared plus 2p. Again, consider the greatest common factor. This is all being multiplied. Greatest common factor in the p squared plus 2p is going to be p. You take the p out. As far as what remains, you've got p plus 2. Considering the denominator, pushing all of this stuff together, we've got p times. Well, notice the p squared minus 4 is the difference of two squares we can factor. That would factor to p minus 2, p plus 2. Now that we've factored everything out, we can start comparing common pieces between numerator and denominator. Any common pieces we see, we can divide out. So I see a p minus 2, a p minus 2 is quantities. I can divide those out. And as I divide them out, I understand a 1 maintains those positions, right? The p's, I could divide those out. And the quantities of p plus 2, I could divide those out. Now we've taken out all these factors. Looks like all that remains is a 3, right? So our resulting product would just be 3. With the division, if it's the same as the multiplication, the one thing we got to remember is that to turn this into a multiplication problem, we got to take what we're dividing by and flip it. So if I follow a similar procedure to what I just did on the last problem, knowing I'm going to push all this stuff together, form a great big fraction here where I'm comparing factors on the top and factors on the bottom. Starting with what I have on top over here, I've got d squared plus 4d. I could take a d out of that. Be left with d plus 4. Multiplying that onto this 2d minus 2 is going to shift to the top because of the division. That's going to shift to the top. I could take a 2 out of that. Be left with d minus 1. All right, in our denominator, over here we've got d squared plus 3d minus 4. We could factor that out. We consider the factorization for that quadratic. Got d times d, got 4 times 1, right? It's going to be a plus 4, it's going to be a minus 1. There's my factorization for the quadratic. And then recall that this d cubed is shifting down here. All right, comparing top to bottom now. Looking for some quantities that are shared. Got some d plus 4 factors. They divide out. Got some d minus 1 factors. They divide out. We've got this d right here. We've got this d to the third. So we could divide this d out, understanding we're going to divide the d into this d to the third right here. If we divide the d into the d to the third, well, we just have d squared left. So what's left over? Looks like we got 2 in the numerator. We've got d squared in the denominator. All right, so we've got another multiplication problem. We've seen how the first couple work. We know where we're going with this. Okay, we start factoring whatever we can. We've got x cubed minus 8. That's a difference of 2 cubes. So x cubed minus 8 factors to x minus 2. And we have to tack on that trinomial that goes with that factorization for a difference of 2 cubes. That trinomial is going to consist of this first term squared, x squared, the product of the 2 and the x added on, and then the last term squared here, so plus 4. That's the factorization for the difference of cubes. Moving on to the x cubed plus 2x squared. If I factor out the greatest common factor there, x squared pops out. As far as what's left, we've got x plus 2. In the denominator, we start with the x cubed minus 4x. Greatest common factor would be x that I take out. Now that leaves me with, think about where you're going here, x squared minus 4, right? X squared minus 4 is a difference of 2 squares. So if we could take care of all of that at one time. Factor is a difference of 2 squares as well. We took the greatest common factor out, factor is the difference of 2 squares, all in one step. And then what else do we have here? Well, we got the x squared plus 2x plus 4. Appears to be something factorable. Really, it's not. And if you look at common factors that will be shared between numerator and denominator here, we'll be able to get rid of that piece anyway. So this piece is gone. We divide it out, leaving ones in those positions. Other quantities that are shared, you've got x minus 2, x minus 2, x plus 2, x plus 2. And then we've got an x here we can divide into itself. If we divide into the x squared up here, leaving us with one of those x's. When all is said and done, the product is just x. All right, so on this division problem, we'll turn this into multiplication by appreciating that we're going to multiply by the reciprocal here, the second fraction. Factoring that n to the 4th minus 1, that's a difference of 2 squares, right? So if I factor that as a difference of 2 squares, taking the square root of that n to the 4th to get my lead terms here, it's going to be n to the 2nd. I could say n to the 2nd plus 1, and then it'd be n to the 2nd minus 1, right? Also a difference of 2 squares. So n to the 2nd minus 1 would be n minus 1, n plus 1. So if you need to, initial step, n to the 2nd plus 1, n squared minus 1. And then next step, break it down to what I have up here. Okay, we've got this quantity of n minus 1 squared. So really no factoring to be done there. I'm sorry, that's going to be the new denominator. I've got n squared minus 1 right here. I've got to factor that out. N squared minus 1 is now shifting to the top. So we've got n minus 1 times n plus 1. Now moving to the bottom. N squared plus 1, not factorable. Cannot factor a sum of 2 squares. So we leave that as its own quantity. Now I look at this n minus 1 as a quantity squared, which is shifted down to the denominator. I could leave that as n minus 1 quantity squared, or state it as n minus 1 times n minus 1 if I want to spread out the factors to have a better look at things. Sometimes with those quantities, the way those are written, when they're raised to a power like that, it's a good idea to spread things out to see just how many factors you're playing with. Because now as I start to divide out the common factors between numerator and denominator, you've got this n squared plus 1, and divide that out. Got an n minus 1 and n minus 1, divide those out. Another n minus 1 over here, n minus 1. Dividing out everything I can, we're left with, well, n plus 1 times n plus 1, right? So we could say n plus 1 is a quantity squared. All right, if we try this one, follow the same routine. Start with the greatest common factor in the x squared minus 2x. The greatest common factor being x, we take that out, x minus 2 is left. Not much you can do with x plus 3, so I'm going to leave that as a quantity of x plus 3. Shifting now to the denominator, we've got an x over here. That is what it is. We've got this quadratic idea. All right, so with the quadratic, can we factor that out? Can we break that up? Well, it's a little backwards to what we're used to, right? But we can still handle this, right? If we reverse the FOIL process, we can still handle this. In the ladder positions, because I'm subtracting the x squared at the end, we'll have the x's in the ladder positions. And in the initial positions here, these lead positions, we got to have stuff that multiplies to give us that 6. So if I try 3 and 2, to sync this up and create that negative x in the middle, it would have to be negative over here, positive there, right? All right, so let's see how we did as far as common factors are shared between the numerator and denominator. If you look at the x's, right, this x, we divide those out. All right, I'm going to move to the x plus 3 next, because x plus 3, 3 plus x, that's the same thing, right? So these are the same factors. But the x minus 2 and the 2 minus x, are those the same? No. In fact, those are opposites. Whenever you divide opposite values, what do you get back? If I take negative 4, I divide by 4, those are opposite values. What do I get back? Negative 1, okay? So normally, we've gotten this habit where we divide these ideas out and we're left with 1s, right? Well, in one of the positions, I need a 1. In the other position, which we could say is the opposite one, I need a negative 1. Not going to put negative 1s in both, because negative 1 divided by negative 1 is positive 1. I'm just going to put a negative 1 in one of those positions when I'm canceling out the opposite expressions. So when all is said and done here, negative 1 is all that's left.